Um, Hello everybody. This is Adirane, and um, I'm a junior at SPHS, and I'm currently taking AP Physics C. And I would just like to thank you for coming to our third session this afternoon. And I'd just like to thank you for trusting my knowledge, um, for helping you prepare for the AP exams. I really hope that this helps you, me, and all of us ace this unique situation. And I really think that these live sessions will help us be the most prepared for the AP exams, which are fast approaching. Okay, um, without further ado, let's begin with our lesson today. We will be looking at the AP Physics C mechanics portion of the exam. So we're going to be looking at a mechanics free response question. And more specifically, we will be looking at the first question of the 2004 AP Physics C mechanics exam. Okay, so I will be working through the question step by step. And if you do have any questions about a particular step I did or a particular concept that I used while I'm working, any question whatsoever, I kindly suggest that you use the chat feature in the Zoom meeting. There's a group chat feature at the bottom. You can type in your question there, and after each and every part, I will look at the chat, I will check the chat, answer any questions that appear to the best of my ability. Okay, so without wasting any more time, let's get started. Okay, so this is the first question that is part of the AP Physics C mechanics exam. And let us read the question carefully. Okay, let's just read the question. A rope of length L is attached to a support at point C. A person of mass M1 sits on a ledge at position A, holding the other end of the rope so that it is horizontal and taut, as shown above. So taut basically means it's as tight as possible, maximum tension. Okay, so it's not loose. Okay, so it's horizontal and taut, as shown above. The person then drops off the ledge and swings down on the rope toward position B, on a lower ledge where an object of mass M2 is at rest. At position B, the person grabs hold of the object and simultaneously lets go of the rope. The person and object then land together in the lake at point D, which is a vertical distance L below position B. Air resistance and the mass of the rope are negligible, so you can ignore that. Derive expressions for each of the following in terms of M1, M2, L, and G. Okay, so we see it's a pretty involved situation. Okay, so let's try to visualize, okay? You might start to visualize already. So you have your person swings down and sort of picks up the object, collides with the object, and lets go at the exact same time, and both the person and the object will fall to this point at D. Okay, so let's start with part A. What is the speed? They ask us to find the speed of the person just before the collision with the object. So more specifically, they are asking us to find the speed of the object right over here, right before you hit the object. Okay, so how do you approach this? Well, one thing I would notice is, where is the person initially? Because when you are changing height, there is a change of potential energy. taking place. So when you have a problem that involves a change in height and they ask you to find the speed, then your first instinct should be using the law of conservation of energy and noting that air resistance is negligible, which means that energy will be conserved during the entire swing. Okay, so let's see, at position A and position B, okay, how much potential energy does the person gain or lose? So first you have to ask, is the potential energy increased or decreased? Well, clearly it decreases because not only is the person at a lower position at position B, but the person is also moving with a speed at position B that we're asked to find, meaning that some of the potential energy must be transferred into kinetic energy. Okay, so what I'm basically saying is that at point A, okay, so at point A, we see that the gravitational potential energy, okay, let's move here. The gravitational potential energy must be equal to the kinetic energy. Must be equal to the kinetic energy. Okay, so what is the change in the gravitational potential energy? Okay, so actually the more correct equation will be the change in the gravitational potential energy would be the kinetic energy. Okay, because the person is still above the ground, but whatever potential energy that that person has lost during this swing must be replaced by kinetic energy, must be transferred into kinetic energy in order for the law of conservation of energy to be satisfied. Okay, now the change in potential energy is just the mass times g, which is a constant, okay, the gravitational acceleration times the change in height. Okay, what is the change in height from A to B? Well, it will be the length of this red segment over here. Okay, you're initially here and you end up over here. Well, the length of the rope is L, okay? And because it's taut, it's at its tightest, the rope can extend. So what we can say is that this red segment is also of length L. It's also of length L. So essentially, our kinetic energy must equal M1, that's the mass of the person, times G times L. Okay? Now, this kinetic energy is equal to 1/2 M1 times V squared. Okay? So that is the formula for kinetic energy. So what we're basically saying is that this expression must be equal to this expression. Now, how do we solve this equation for V? Because that's what we want to find. Okay? At the bottom, it will be moving with the speed V. What will be V? Now, you can notice easily that the M1s cancel, meaning that the speed is not dependent on mass. Okay, we get 1/2 V squared equals GL. Okay, we multiply both sides by 2, and that gives us V squared equals 2GL, and we take the positive square root. We take the positive square root, and we get V is equal to the square root of 2 times G times L. 2 times G times L. All right, that will be our speed at the bottom, okay, at the bottom at point B, right before colliding with the object. Okay, does anyone have any questions so far at all? Okay, so let's see if we have any questions. Okay, any questions at all? Okay, it looks like there are no questions. I can wait for a minute just to wait for everyone to grasp the solution. This is not a super hard part because it's a straightforward application of conservation of energy. Okay, so let's move on to part B because I don't see any questions over here. Okay, so we're gonna move on to part B, and part B asks is, what is the tension in the rope just before the collision with the object? So right before, at this black point on the diagram, what is our tension? Now, tension is a force, so it suffices to draw a force diagram, a free body diagram. Okay, so a free body diagram basically diagrams all the forces that are acting on our object, on our person. Okay, so we have our free body diagram over here. Okay, so obviously we have the weight of the person, which is holding him down. That's the force of gravity. So we have our weight and we have our force of tension. Okay, so we have tension over here. We have weight pointing downward. And when the object is at its bottom, okay, it's moving, but how would we find this tension force? Now, you might think to just equate the weight and the tension, but that's not the full story, okay? Because at this lowest point at position B, right before our collision, the person is undergoing motion in a circular arc, okay, as shown by this dotted blue path. So, in effect, over at position B, our person is undergoing uniform circular motion at that instant. So at that instant, so you have to be very careful. It's not uniform for the entire path, but at that instant, you can treat it as uniform circular motion, meaning that there has to be a centripetal force. There must be a centripetal force at the bottom, at point B, that is maintaining its motion, maintaining the person's motion right before the collision with the object at point B, the collision of the object of mass m2. Okay then, so what I basically imply is that there is centripetal force and we need to utilize the centripetal acceleration. Okay, so the force has to provide a centripetal acceleration. Okay, now, how do we go about solving for the tension knowing this information? Okay, so the centripetal acceleration is v squared over the radius of the path. So our mass of the object, m1, times v squared over L. That's the radius of the circular path, the circular blue dotted path that I outlined. Okay, so m1 v squared over L, and that becomes 2m1 gl over L. We cancel L from both sides, from the numerator and the denominator, and we get the net centripetal force has to be equal to 2m1g. Okay, now the tension force is toward the center of the circle. Okay, it is toward, let's use green. The tension will be pointing this way. This will be tension. So tension is trying to maintain in a circular path, while the weight is trying to get it out of the circular path. So we're going to treat tension as positive, okay? Because by convention, this inner seeking forces will be positive, okay, in order to maintain the circular motion. Okay, so what we have then is the tension minus the weight m1g, that's the formula for the weight, equals 2m1g. And now we get our tension by adding m1g to both sides. We get tension is 3 times m1g. Okay, that's how you that's how we approach this problem. Okay, so I'm gonna open up for any questions on this part. This part dealt primarily with the idea of centripetal circular motion. Okay, so I'm gonna open up for any questions right here. Okay, do we have any questions at all? Okay, looks like we don't have questions. Again, if you have any question whatsoever, you don't understand what I did or any step that I performed, please feel free to enter into the chat what questions you may have, so that you can leave the session having a better understanding of the concepts involved. Okay, so I don't see any questions, so we're going to move straight to part C. Okay, part C asks for the speed of the person and object just after the collision. So what we're going to be doing, is after the collision, we have a combined person and object system. So because there are no external forces acting on the person and the object before and after collision, we can assume that momentum is conserved during the collision. And generally, when you deal with collisions, momentum will be your number one choice, mainly because it is conserved. It is conserved for all masses. Okay, so what we're going to be doing is applying conservation of momentum to this collision. So we have our initial momentum must equal our final momentum. Okay, so we have m1 v naught. I'm going to make v naught the speed of the person before the collision of the object, before the collision with the object. And that has to equal the combined mass of the person and the object, m1 plus m2 times vf. Now, v naught we determined as square root of 2gl. That is the speed from part A right before the collision. So what we can do is write this as m1 square root of 2gl has to equal m1 plus m2 times vf. Okay, so now using this information, we can divide by this sum n1 plus m2 to get vf equals m1 over m1 plus m2 times the square root of 2GL. Okay, m1 over m1 plus m2 times the square root of 2GL. This is probably the easiest portion, just because it's very straightforward application of conservation of momentum. Momentum has to be conserved because there are no external forces giving an external impulse to this system. There's no forces that are changing the momentum of M1 prior to the collision, meaning that we can equate the two sides and solve for the final velocity, the final speed of the object just after the collision. Okay, so now let me check if there are any questions. Are there any questions so far? Okay, it's again, momentum is usually used, conservation of momentum is usually used when you're dealing with a collision of some sort, okay? And the principles of momentum are quite easy, okay? And because they're conserved, we can see easily what the final speed will be, because the momentum has to equal the same. So essentially, it becomes a simple equation. Okay, now what we're gonna do is move to part D. Okay, and part D asks for the ratio of the kinetic energy of the person object system before the collision to the kinetic energy after the collision. So we're looking for the ratio of the initial kinetic energy over the final kinetic energy. We're looking for this fraction. Okay, now, how do we go about doing this? Well, the initial kinetic energy right before the collision, while the only object that is moving is the person of mass m1. Again, before the collision, our second object of mass m2 was at rest at position B. So it has no kinetic energy, does not contribute to the initial kinetic energy. So we have 1/2 times m1 times v naught squared. 1/2 times m1 times v naught squared. And our final kinetic energy will be 1/2 times the combined mass of m1 plus m2 times vf squared. So essentially, we're trying to find this ratio, and we're going to try to simplify it as much as possible. Now, what we're going to do is cancel out the 1/2. Okay, we're going to cancel out the 1/2, and essentially, we are turning this into an algebra problem. This is more of an algebra problem, a math problem, okay, with all of the simplification. So we have m1 v naught squared over m1 plus m2 vf squared. Now, v naught squared is 2GL, okay? So, right, like doing the bar first, we have m1 times 2GL. Okay, what about the bottom? The bottom, we have m1 plus m2, and vf squared gives us m1 squared. Okay, vf is the speed we found in part C. So again, we're just squaring this. m1 squared times 2GL over m1 plus m2 squared. So essentially, we try to simplify this. We just have to try to simplify this as much as possible. Now, this m1 plus m2 cancels with this squared. So essentially, we have m1 times 2gl over m1 squared times 2gl over m1 plus m2. And in situations such as these, I like to multiply by the reciprocal when dividing by a fraction. So what we're trying to do is multiply by m1 plus m2 over m1 squared times 2gl. And now it's a lot easier to visualize. The 2gl's cancel, the m1 and this square cancels, and we're left with our final ratio, m1 plus m2 over m1. So note that the ratio of the kinetic energies, okay, shows that there was more kinetic energy before the collision than after. And it makes sense. It makes sense because the collision was inelastic. There had to be a loss of kinetic energy because there's work done in picking up the object and holding the object and colliding with the object. So we have more initial kinetic energy, but what's kind of cool to me is that this ratio is only dependent on the masses of the objects. It's not dependent on the length of the rope, and it's certainly not dependent on the speeds. It's only dependent on the masses. And looking at the equation, if m2 was 0, so basically there's no collision, then m1 over m1 would be 1, so energy would be conserved. So in this case, m2 is non-zero, so we don't have energy being conserved, but it's a cool fact to look over. Okay, now what I'm going to do is, okay, let's see if there are any questions. Okay, so this was just an algebra problem at heart. Okay, essentially, we just have to simplify this monstrous fraction. Okay, and use the formulas of kinetic energy and just simplify until we can't simplify anymore. Okay then, so do we have any questions so far on any of the parts or on this part? Do you have any questions so far? Okay, so it appears that there are no questions. There are no questions. So we're going to move on to the final part. We're going to move on to the final part, and that is part E. Part E asks for the total horizontal displacement x, okay, of the person from position A until the person and object land in the water at point D. Okay, so basically it's asking us to find the length of this. How far from your initial position all the way up here do you land? Okay. Now, we see that this first section, which I'm going to highlight in yellow, we already know is L. So what we basically need to do is find this section. This distance over here, which I'm going to call D. Okay, what we need to do is find D, and then we can add L and D to get our final length X. Now let's move over here. Okay, now, how this basically becomes a kinematics problem at this point. okay? Because you're in the air, you are not constrained by the rope, and essentially you're moving with this horizontal velocity, Vf. Remember, you collided with the object, so Vf will be your speed, not V naught, okay? After the collision, you move horizontally at Vf, and you're trying to find this horizontal distance d. Now, how do we approach this? Now, we need to see what kinematics equation we should use, okay? Because there are a lot of kinematics equations, but we need to see what we know and what we don't know. So what do we know? We know the initial velocity, okay? V naught, okay? And keep in mind, this is not the same V naught from part A, okay? This is not the same V naught from that. This is just a notation, the convention that we use for solving kinematics problems. So we have V naught, okay? We have our acceleration in the downward direction, which is g. There are no forces acting in the x direction, okay? So in that direction, acceleration is 0. So we have our acceleration. We don't have time. We don't have our final velocity. So what I can do is try to solve for the time, because if you remember from kinematics, we usually like to solve problems in terms of the x and y components, okay? So we solve for a quantity in one component, the motion is independent of each other. So if we solve for the quantity in one direction, okay, and it's common in both components, we can use the same quantity from one component and apply it to the other. And you might know which one I'm talking about, okay? While Vx is, while the x component of the velocity is only related to the x component, while the height in the y direction is only related to the y component, there is one quantity that is common to both components, and that is time. So it makes sense that we solve for the time it takes to land to point D. Okay, try to find this link between the x direction and the y direction. How do we do that? Well, we have two principal equations, Vf equals V naught plus AT, and height equals V naught t plus 1/2 AT squared. Okay, so which one should we use? Well, we don't know the final velocity, but we know the height in the y direction, so we can apply this in the y direction. We know the acceleration in the y direction, and because we start off moving horizontally up here, okay, this is in the horizontal direction, the component of the initial velocity that's in the y direction is 0. There is no initial velocity in the y direction. So in fact, that is exactly what we're going to do. Okay, that's exactly what we're going to do. So v naught y is 0. So that saves us a lot of time. We don't have to deal with a terrible quadratic equation. We can deal with the simpler one. Now our height, how far do we fall? Okay, and I'm going to choose downward as positive. Okay, I like choosing a direction that allows me to have as many positive terms as possible. It simplifies the math. Okay, so downward positive, you're falling down a distance of L in the y direction. Okay, so this will be L, so our height essentially is L. So L equals 1/2, and our acceleration, the y direction, is g, and it's downward, and I pick down as positive, so it's positive over here, 1/2 gt squared. So if we multiply both sides by 2, 2L equals gt squared, and dividing by g and taking the square root gives t equals the square root of 2L over G. All right, that's good. Now, what is our distance? Now we go to the x direction. D equals Vx times t, and in effect, Vf times t. Okay, where Vf is the velocity we found in part C. Okay, so because all of Vf is in the x direction and this x velocity is constant, now we get m1 over m1 plus m2 times the square root of 2gl. So I'm going to do all of these operations inside the square root. So 2gl times the time, which is the square root of 2l over g. And now we see that a lot of these terms end up canceling. Okay, g cancels, and this combines 2 times 2 is 4. Okay, and L times L is L squared. So we have square root of 4L squared. So essentially our D is 2m1L over m1 plus m2. So what is our final X? Well, our final X is equal to L plus D. So that is, if we use a common denominator, we have m1 plus m2 L plus 2m1L over m1 plus m2. Okay, and we get our final answer as 3m1 plus m2 over m1 plus m2L. That is our final answer. Okay, and as you can see, this is essentially a kinematics problem in disguise, part E. And you can see that it's dependent on the length L of the ledge and the string and the masses. It's not dependent on the velocity, okay? It's just dependent on the masses and L. Okay, so we're gonna see if there are any final questions. Okay, so do we have any final questions on anything so far? Okay, so seeing as there are none, okay, we don't have any questions, right? And this problem was pretty involved. It tested conservation of energy. Okay, it tested uniform circular motion and centripetal forces, Newton's second law, conservation of momentum, algebra skills in part D, kinetic energy, and your kinematics knowledge. So this was a very involved problem. So it seemed a bit difficult. It really wasn't that hard because you worked through step by step and each part built on the other until you finally were able to combine all of them together in part E and try to find this distance X. Okay, thank you. Thank you so much for coming. Thank you so much for coming to the session, and I'm really glad for all of you who are able to make it, able to join the session. Okay, please leave feedback and suggestions on today's session. I will try to upload the video on Facebook, a copy of the video. I will also put on YouTube in case something goes wrong. I've been trying to upload it onto Facebook. I still can't for some reason, but I will try to put it onto YouTube so that everyone can access it. Please leave comments of what I should cover next, either below. Next session will be electricity and magnetism. Okay, so all right, so thank you everyone for joining. See you next time. Goodbye.